Hello, welcome to Q in Motion's course on understanding electricity and electronics devices. This is our third class. Before we move on, let's review what we've seen in previous classes. So last class, we studied DC and AC. DC was direct current, where polarity is always the same. And AC is alternating current, where polarity changes several times per second. We also looked at voltage sources like batteries, outlets, and power supplies. We also studied Ohm's law and resistors. Resistors are devices that are intended to insert resistance in a circuit. And today we're going to have a look at why is it that we may want to do that. The other thing we studied last class was Ohm's law. That relates voltage, current, and resistance through the equation V equals IR, or voltage equals current times resistance. In today's class, we're going to study Kirchhoff's laws. We're going to have a look at LEDs and also at switches. Let's start with Kirchhoff's laws. Kirchhoff's laws are two laws. One relates to current and another one relates to voltage. Let's start with Kirchhoff's current law, or KCL. A simple formulation states all current entering a node is the same as all current exiting a node. It has a more formal statement, but I feel that this one helps better understand it. Now, what does this mean? Say it says all current entering a node. A node is where several branches of a circuit meet. It's like this one here. So we have 1, 2, 3, and 4 branches meeting in this node. So if the current entering a node, in this case, assuming all these arrows are correct, we have I2 entering this node and I1 exiting on this branch, I3 exiting on this branch, and I4 exiting on this branch. So KCL, or Kirchhoff's current law, simply states that I2, the current entering a node, is going to be equal to I1 plus I3 plus I4. Simple enough, right? Okay, let's move on to Kirchhoff's voltage law now. The formal definition says that the sum of all voltages around the circuit loop is 0. So let's take this one as an example. We have a loop here, which is a path where we can go around, right? And let's start at this point. So here, if we add all the voltages and keep in mind the signs here, if we go from minus to plus, we're going to add. If we go from plus to minus, we're going to subtract. So let's start at 0 here, and we start plus 5, right? Minus 0.5, that is 4.5. Minus 2.5, that is 2. And again, minus 2, that's back to 0. So if we go around this loop and we add all the voltages with their proper signs, we're going to get 0. There might be an easier way to understand this or to state this voltage law. So the voltage gain from a source equals the sum of voltage drops on the devices around the loop. What does this mean? So we have a loop here. And let's start at this point, which is ground, which is convenient. And again, if we go through this loop from this point all around back to this point, we start with 0, and we gain 5 volts because of this voltage source. And then voltage is going to drop on this resistor 0.5 volts. Then it's going to drop another 2.5. And then it's going to drop another 2. And when we go back here, we're back at 0, right? So here's mathematically, the voltage on R1 is 0.5, on R2, 2.5, on R3, 2 volts. And when I add all those up, I end up with 5 volts, which is the same voltage as the source. All right. So let's have a quick look and see how this KVL or Kirchhoff's voltage law can be used to solve a circuit. Let's assume this problem. So we have the circuit, a 5-volt DC source, and then a resistor whose value we want to calculate. We don't know what it's going to be, but we want to have 10 milliamps flowing through this device D, and we know that this device D has a voltage drop of 1.7 volts when 10 milliamps flow through it. Okay, so how do we do this? First thing is we use KVL, or Kirchhoff's voltage law, and we say that the voltage across R1 is going to be 5 volts, which is the voltage from the supply, minus 1.7, which is whatever we lose here. So 5 minus 1.7, that is 3.3. So if I have 5 volts in this supply and this one is dropping 1.7, this resistor has to drop 3.3. Now, we have the voltage 3.3 and we have the current, and we have to find out the resistor. And to do that, we can use Ohm's law. Remember from last class? So R1 is going to be VR1 over IR1, where the resistance is the voltage divided by the current. In this case, the resistance of R1 is going to be the voltage, the 3.3 volts, divided by the 10 milliamps. And if we do that math, it's going to be 0.33 kilo ohms or 330 ohms. So in this circuit, if we want 10 milliamps to flow through it, we're going to have to put a resistor of 330 ohms. All right. Let's have a look now at LEDs. LEDs are light-emitting diodes. This is the symbol for it. This triangle with a bar here is the symbol for a diode that does not emit light. But those are kind of boring, and we're going to see those on a different class. But today we're focusing on LEDs, which are light-emitting diodes. So we draw the symbol as a diode with this arrow or this lightning bolt, if you want. That symbolizes an LED. So LEDs are diodes that are optimized to emit light, and they come nowadays in pretty much any color. They can even be infrared and UV or ultraviolet. So the site where the triangle is called the anode, and it's for the LED to turn on, it has to be positive. And the site with the bar is called the cathode, and it's symbolized with the letter K, although cathode is written with the C. And that's the negative side. Physically, this is what an LED looks like, but the anode is usually longer and the cathode is usually shorter. Also, on the base of the diode, the cathode is flattened here. If you have a look here, the anode is rounded. This should be a full circle, but instead of being a full circle, it has like a flattened side here on the cathode. So those are two ways to identify which one is positive and which one is negative on an LED. But these rules may not be universal. So check the data sheet to be sure. If you don't have the data sheet, this is probably a very good guess. So how do we turn on an LED? Like we said, the anode has to be connected to positive and the cathode to negative. The typical current from an indicator LED, which is the little red LEDs like this one here, is about 10 milliamps. If you have an LED that's actually a lamp that is actually used for lighting, for replacing a light bulb, the current is going to be much higher. But a little indicator LED typically lights up at 10 milliamps. The voltage drop at this current depends mainly on the LED color. And this may be surprising for you, but yes, it's because of the physical structure. It requires different voltage to turn on. Different LEDs are made from different materials internally, different colors, I mean. So a red LED will have a voltage drop of approximately 1.9 volts, a green LED about 2.3, and a blue about 3 volts. And these are rough guidelines, so you should check your data sheet to be sure what the voltage drop is. But again, if you don't have a data sheet, or if you just want it to turn on and it doesn't really matter if it is too bright or too dim, just go with these values. So let's have a look at how we can calculate a resistor here for a circuit to light up an LED. Like we said, we normally want the LED to be turned on with about 10 milliamps. If you put 5 milliamps, it's going to turn on, but quite dim. If you put 20 milliamps, it's going to turn on fairly bright. If you put 50 milliamps through an LED, you may be damaging it. So 10 milliamps, again, you can check the data sheet to see what the manufacturer recommends for current, but 10 milliamps is a fairly universal value. So our problem would be if we want to turn on this green LED with a 5-volt power supply, we know that we want about 10 milliamps going through the LED. So let's calculate R1, that resistor. How much is that going to be? If you recall the problem about KVL or Kirchhoff's voltage law, this is very similar, right? Only in that problem we had a device here that's taking 1.7 volts, and now this is a green LED. So a green LED, we saw in the previous slide that it would take about 2.3 volts when 10 milliamps go through it. So this is our circuit, 5 volts, a resistor of unknown value, and 10 milliamps, and 2.3 is going to be taken by the LED. So the first thing we do, we use KVL, or Kirchhoff's voltage law, to calculate the voltage drop on the resistor. If we have 5 volts here and we're losing 2.3 in the LED, we have to lose 2.7 on the resistor. And again, we can use Ohm's law to calculate the value of the resistor. We divide the voltage on the resistor, which is 2.7 volts, by the current through the resistor, which is 10 milliamps, and we obtain 270. So that's our answer, 270 ohms. We put a 270 ohm resistor there, and this LED is going to turn on with 10 milliamps flowing through it. So the fact that LEDs turn on only when current flows in one specific direction means that we could build a little device to detect polarity. In this case, if we build this device with a green and a red LED, and we put a resistor here on the green LED and another resistor on the red LED, and we connect the red wire here and a black wire here, we can use this thing to detect polarity. So how does this work? Well, if we connect a 5-volt voltage source to this circuit with this polarity, what's going to happen? Well, current's going to flow from the positive side of the power supply through the red wire, and then through the green LED, and then back to the power supply here. So the green LED is going to turn on. Now the red LED has its polarity reversed, so positive is going here to the cathode, and negative is connected to the anode, so no current is going to flow here. So we're going to be calling this the correct polarity because we're connecting the red to the positive and the black to the negative, and that will result in a green LED turning on. Now we disconnect this and we connect it back, but we connect it backwards. So the negative on the red and the positive on the black. So what happens here? We have the positive on the black, current flowing this way. Positive is on the cathode of the green LED, so the green LED is not going to turn on, but it's on the anode of the red LED, so the red LED turns on and current completes the circuit back to the negative side. So when we connect these in the incorrect polarity, the red LED turns on. So basically this circuit can detect polarity. You connect it in the correct polarity, the green LED turns on. In the incorrect polarity, the red LED turns on. If nothing turns on, well, there's probably no voltage there, right? All right. So let's see how we can check an LED with a multimeter, right? So we have an LED, and we want to know if an LED is good, if it turns on. And we also want to check which one is the positive or the anode and which one is the cathode. So all multimeters have a diode check function like this one, right? So you put the selector knob on the diode check function, and then you connect the red test lead to the longer leg, which is the one we think it's the anode, and the black to the cathode, which would be the other one, the shorter, right? So that should make the LED turn on, and it also is going to show what the voltage drop is across the LED. We don't know what the current is through the LED. It will depend on the multimeter itself, but this is not going to put a lot of current, probably around 1 milliamp. So the LED is going to turn on fairly dim here, and the voltage is going to be a bit lower than what you would normally have in a circuit. So probably if we pass 10 milliamps through this LED, we're going to have something closer to 1.9 or 2 volts, right? But with this little current, we're going to have only like, we have only like 1.75 or so. So again, if the LED doesn't turn on, just reverse the polarity. It may be that that particular LED or manufacturer or that particular model has the longer terminal is the cathode, but it is unlikely. I don't remember ever seeing one of those. If you want to purchase an LED, what would you look at? First, shape. Whether it's round, square, rectangular, triangular. So they come in many different shapes and also many different sizes, typically around 3 millimeter diameter or 5 millimeter diameter. Those are very common ones for indicator LEDs. Other thing you want to specify is the color, right? You may want a red or a green or blue or whatever. And for some special applications, you may want to select it based on brightness and projection angle. So some of these LEDs project a beam of light that is more focused, and some other LEDs project a beam of light that is more open, wider beam. So usually the ones with the narrower beam are brighter. So those you have to look pretty much from the front, but they're going to be fairly bright. You might be able to project some like a round spot of light with those, whereas others have a wider beam, and those are not as bright, but they can be seen from a much wider angle. So if you look at those from the side, you will see pretty much the same brightness as if you see those from the front. If you want to take a break, this may be a good time. You can hit pause, take your break, and then come back, and we will continue with switches. So what is a switch? A switch is a device that can close or open a circuit. This is a very simple example, right? We have a 1.5 volt battery here, a switch, and whatever device this might be. So this switch here is shown in the open position. So the circuit is open, no current can flow through this. When you close the switch, this makes contact and you have current flowing and the device turns on. So an on-off switch is usually works by opening a circuit and at the battery. So this is an example of an on-off switch. You open the switch, it turns off. You close the switch, the device turns on. Switches come in different number of poles and throws. We're going to see those in a second. Poles are the number of independent circuits that the switch will open or close. And throws are the number of positions where the switch can make contact. Don't pay too much attention to these definitions. We're going to see those in a minute. So these are switches with different number of poles. This is a single pole switch, right? It can open or close one circuit. This is a double pole switch, which is two single pole switches, but mechanically linked. So this dotted line here means whenever one of these opens, the other one opens, and whenever the other one closes, the other one closes. And this is a 4-pole switch. So whenever you activate it, you're closing 4 switches at the same time, 4 circuits at the same time. Whenever you turn it off, you're opening 4 circuits at the same time. Okay. This is to illustrate the different number of throws. This is something that we call a single throw normally open. So this means that this is normally open, right? In case of being a button, a push button, this is normally open. When you push it, it closes. This is the same thing, only when we draw the symbol in a closed position means normally closed. So if this was a push button, whenever you push the button, you will be opening the circuit. So this is a normally closed. And these are single throws because they make contact in only one position, right? So it's open or making contact in one position. This is making contact in one position or open. This is an example of a double throw switch, which is this middle point can connect to this circuit or this circuit. So in one position connects to this circuit and other position connects to this circuit. For instance, if we want, we could have a mechanical switch that one position connects headphones and the other position connects speakers. So these could be done with a double throw switch. And this, again, we can extend this, and this would be a 4-throw switch. These are normally rotary switches, and this middle point can make contact with any of those. So this would be a selector switch to select one of 4 different functions in some piece of equipment, for instance. Okay. So what do these switches look like? They come in all kinds of sizes and shapes. We have an example here of an SPST. SPST means single pole, single throw, push button. And I'm saying that this is normally closed. There's really no way of knowing just by looking at the picture that this is a normally closed. But if these were normally closed, it means that these 2 contacts are connected together, and when you push the button, they will open. This is an SPDT or single pole double throw toggle switch. This is the middle point. Whenever the lever is on one side or the other, this middle point is going to be making contact with this terminal or this other terminal. Next, we have this one here. This is a DPDT push button. So it seems to have like a lot of terminals, but these are just for mechanical support, and this one the same. So these are connected to the case. They don't have an electrical function there. So it actually has 1, 2, and 3 terminals on one side, and 1, 2, and 3 terminals on the other side. So this is a double pole, double throw push button. These 3 terminals here would be the same as these 3 here. And this would be duplicated over here with these other 3 terminals. So it's like 2 of these switches glued together and activated by the same button. Next, we have this SPST limit switch. It's a single pole, single throw, and I'm saying it's normally open, but again, you have to check the data sheet, or maybe it may be printed here on the side. These things are used to detect position of moving parts. So these will normally be attached to a frame, and a moving part, when it moves to one end, it will hit this switch. And the controller for that device is going to know that that's the end of the motion, and it will not allow, for instance, the moving part to move any further. This is used, for instance, in printers. So the print head on each end will have one of these. So if the print head, for whatever reason, is driven against one end of the normal travel, it will hit one of these. The controller will know, hey, this is as far as you're going to go. I'm going to shut power to you, or I'm not going to be allowing you to move any further in this direction. If you want to move in the opposite direction, that's fine. Okay. Next here is a DP40 rotary switch. So it's double pole, 4 throw. So 4 throw will have actually 5 terminals. You cannot see those because of the angle of the picture. You only see 4 on this side and 4 on this side, but there's a 5th behind here and a 5th behind this one. So this switch has 4 positions. It's printed here, C1, that would be common 1, and then position 1, 2, 3, and 4 over here. The C2, it's the common for the other pole, and it's going to have positions 1, 2, 3, and 4. Okay. So if you're a bit older, like I am, and used to have an old stereo that had maybe a selector switch where you could select whether you would listen to the radio, to the record, or to the cassette, or maybe to an auxiliary input, you would have something like this, a 4-position or 4-throw switch, rotary switch, where you would select which device you want to listen to. And internally, this would be a double pole because this is stereo, right? So you would use one pole for the left channel and another pole for the right channel. And finally, we have an SPST wall switch. That is the regular switch that we use to turn on and off the lights. So how do you specify a switch? If you want to buy a switch, what do you have to look at? So the first thing you want to specify is the mechanical actuation, whether it's a push button, a tactile switch, a limit switch, rotary, toggle, etc. Right? So mechanically, how you're going to be actuating it. The next thing you want to specify is the contact configuration, how many poles and how many throws it's going to have. And the last thing you may have to look at, it's the maximum contact current and voltage rating. You cannot, there's a limit of how much current and voltage you can switch with one of these. If you're gonna be building a low current, low voltage circuit, this really doesn't matter. But if you go above 1 amp, or if you go above 30 volts or something like that, you should make sure that your switch actually can handle those levels of current and voltage. As an example here, we have pretty much all the information we want printed on the switch itself. So this one can switch up to 15 amps at 125 volts AC, or up to 10 amps at 250 volts AC. This DPDT, it has 1, 2, 3, 4, 5, and 6 terminals. So these two are the common, and this one are the two throws. This is one pole and this is another pole. All right. So how do you test a switch with a multimeter? Well, we use a continuity function in the multimeter. It's symbolized with a beep, with this kind of a sound wave here, right? So what it does, it measures resistance, and if the resistance is less than a set value, say 10 ohms or 100 ohms, the meter will beep. So you don't have to look at the display. You just hear the meter beeping. In this case, we have the probes connected to the common, and one of the contacts for the normally closed contact. So whenever this is not being actuated, we have continuity between these two terminals. And this is shown here with a very low resistance of 0.3 ohms. And you cannot hear it, but this meter was beeping at the time. Okay, so let's have a look at some circuits that we can build with switches. The most basic one is an on-off switch with a single pole, single throw switch. So we have the battery, as we said. We open the circuit, the device turns off. We close the circuit, the device turns on. As simple as it gets. Next one is what we call a three-way switch. And this is done with two SPDT switches, so single pole, double throw. This means that this switch can be in any of two positions, and this switch can be in any of two positions. These two switches are independent. There's no dotted line connecting both, so you can have any of these in any position. So we have a battery or a power source, and the way it's shown here, we have the device turned on because this one is on this contact and this one is on this contact, and the device turns on, so the circuit is closed and we have current flowing. So if we move this to the other position, the device will turn off. And while this one is on the bottom position and we move this one as well, the device will turn on again. So this is what you call a three-way switch, or a staircase lighting sometimes. Now, whenever you want to control the light from two different positions, from two different locations, you can build this circuit. So if both switches are in this position, the light turns on. If you move this one, you can turn it off, or if you move this one, you can turn it off. And if this one is off, you can move this one and turn it on from here. All right. So that's how that works. Next, we have this polarity reversal circuit, which is made with a DPDT or double pole, double throw switch, which is the kind of switch we have here. How does this work? So we have a power supply or a battery, right, with the positive and negative side. When the switch is in this position, the positive terminal is connected over here to the top of the device. It's also connected to this wire, but this wire goes nowhere, so it has no effect. The negative side of the battery is connected to the bottom side of the device. It's also connected here, but it doesn't matter because this wire goes nowhere. So when the switch is in this position, we have positive on top of the device and negative on the bottom of the device. What happens when we toggle the switch to the other position? So what happened is the positive side now is connected over here to this wire that has no effect, but it's also connected to the bottom of the device. So the bottom of the device, which was negative when the switch was in the other position, it's now positive. And the negative side of the battery is connected over here to this wire that has no effect, but it's also connected to the top of the device. So depending on the position of this switch, we would be reversing the polarity on this device. So what's the usefulness of this? Well, when we see DC motors later, we see that the direction of rotation of the motor depends on the polarity. So this configuration could be used to make the motor turn in one direction or the other direction. All right. So these are all three circuits here. So let's recap on what we've seen today. So today we've seen Kirchhoff's law. We have two laws. One is the current law and the other one is the voltage law. The current law states that the current entering the node is the same as the current leaving the node. And the voltage law says that the sum of voltages around the loop in a circuit is zero. And these laws can be used to solve voltages and currents in a circuit, and they are usually combined with Ohm's law. Remember, we use that to calculate resistors to turn on LEDs. Then we studied LEDs, and we know that they are available in different colors, shapes, and sizes, and they require the proper polarity to turn on. If you connect the reverse polarity, they will not turn on. Typical current for indicator LEDs is about 10 milliamps, and the voltage drop across them depends on the color. And finally, we saw switches, different configurations of pulls and throws, like SPST, DPDT, and all of those. And we saw that they have different actuation type, can be rotary, toggle, push button, etc. And we also saw some interesting circuits made with switches. And that's all for today. Next class, we will have a look at resistors in series and parallel, voltage divider, variable resistors, and how to calculate electric power. So that's all for today. Thank you for watching and see you next class.